Edge detection is often used as an auxiliary function or filter to perform segmentation. We can use edge detection to directly segment edges and regions of transitions in images, but it is particularly useful when we want to use that as part of another segmentation algorithm. In here we are going to search for transitions of intensities. And there are different transitions that can appear in images. We are looking at discontinuities, and I'm going to mention three of them. The first one is a step discontinuity. That means I start with a value, say a low value here, and then suddenly we abruptly change to a pixel that has a very different value. It could be from a light gray to a very dark pixel or the other way around. This is a discontinuity that is easy to detect. The second one is a ramp. So we do have in the extremes here the two values that are in the step example. However, the transition is not abrupt. We smoothly change from one to the other. And then this is more difficult to detect because if you use regular methods here, what we detect is the point in which the ramp started and the point in which it stopped. Then we have to make a decision where exactly is the border. And the third one is the peak or the edge, and then in this case we have a very narrow ramp that either increases or decreases, but we have a peak and then it goes back to the original or to the previous intensity. It could be an abrupt transition or a smooth transition as it is in this example. In order to perform edge detection, usually we can apply high-pass filters. There are three high-pass filters that are defined in the literature and that are available usually in software packages such as the Laplacian, the Sobel, and the Prewitt filters. After filtering, we have to apply a threshold to extract the edges, because as we have seen in lectures about high-pass filter, what we have as an output is not actually a binary image, but instead a map in which the largest values correspond to higher transitions or to more intense transitions, and lower values to small transitions. So we have to define a threshold to extract the actual edges. And because edge detection is based on mostly derivatives, it can easily degrade with variations and noise. So here we compare noise-free scenarios with noisy scenarios. And we can see that, for example, for this step function here, for this step transition, we will probably have a much harder time trying to detect exactly where the discontinuity happened here. And for this case, in which we have two borders, a white border and a black border here, this is much more difficult when we have noise that hampers the analysis. So it is often common to work with methods that are more robust to noise, either using a pre-processing in order to smooth out the images. The first method that I'm going to mention is the Laplacian, which is an isotropic differential operator. Isotropic means that it considers all directions similarly, and that is a symmetric filter. It means that it is going to detect edges along all directions: vertical direction, diagonals, horizontal, and so on. We can also design filters that are directed, so for example horizontal, diagonal, vertical, and so on, that will capture such edges in specific directions if we need that for the application at hand. A variation of the Laplacian is the Laplacian of Gaussian, that combines a smoothing filter, that's the Gaussian, with a high-pass filter, which is the Laplacian, we have an analytical result that combines both of them in a single equation. So we can use that to compute filters for this purpose. It tends to not only smooth out the results, but also to thicken the borders that were detected. Of course, in here I just defined a threshold. We could vary this threshold or find a better threshold in order to overcome, for example, problems with a texture such as appears here, or a value of larger borders such as the face of the cameraman. Another example comparing different filters is this image that has noise that is mostly distributed horizontally. In this case, because the pattern of the noise is horizontal, if we try to detect filter or detect edges horizontally, we are going to have a very noisy output. We could, for example, use another strategy and detect only 45-degree edges, but we're probably going to miss some of the edges. The Laplacian filter, which is an isotropical filter, includes all directions, but because it also includes the horizontal direction, it also has an output that is noisy. But by using the Laplacian of Gaussian, we have a very fair estimate of the edge with some small noise here that could be, for example, removed by using morphological operators. The Sobel filter is also a well-known method for edge detection that gives more weight to central pixels. So usually the borders are a little bit thicker than in other methods. And here just compare horizontal and diagonal versions of those filters that are easily implemented. Next, I'm going to mention region-based segmentation. In contrast with the edge-based segmentation, instead of trying to find discontinuities, in here we are going to directly, via pixel inspection, to grow regions or to define regions by similarity. So we are going to aggregate pixels or regions by similarity of them. There are two methods that I can highlight here. Region growing in general, that is usually the approach for this method, but there are also such as the split and merge, and that can be also be assisted using a structure such as the quad tree. But I'm going to mention in this lecture just region growing. The idea is that from seed pixels, we are going to allow regions to grow. It could be from a single pixel or a group of pixels. Because of that, those pixels sometimes are also called markers, because they mark initially the regions from which I want to segment the image. And then from those seeds, we are going to add neighbor pixels that have similar characteristics. Important elements to define here is the method for seed initialization. That means we want to define the seeds in some way. The number of seeds per region. How we are going to define the criterion for similarity. And the stopping condition as well. The seeds can be chosen manually by the user, for example, or based on filtering operations or in other algorithms, as we are going to mention in the source code. The similarity can be the intensity difference or also based on local statistic. In the example I'm going to show you later, we are going to use the mean of the region. But we can also use, for example, descriptors of texture, descriptors of color, or a combination of them. The standard stopping condition is to stop doing the region growing when no new pixels can be added to the region. However, when we have two regions that encounter each other, we could have a case in which a single pixel in one iteration belongs to, let's say, a region A, the next iteration to region B, the next iteration to A, and they are going to alternate between different regions, and then we are going to be in an infinite loop, so we want to avoid that. The original algorithm for region growing has recursive nature, but as a tip, it is often safer to implement a virtual stack in order to avoid overflow due to the limit of recursive calls. And here I'm showing you some examples using this very simple approach for pixel aggregation that basically use difference of intensities as a criterion for inclusion. I'm going to start with the first pixel here on the top left corner of the image, and then I'm going to compare that first seed value with the pixel to be inspected or in inspection for inclusion. If that pixel, that new pixel, is sufficiently similar to the first one, then I'm going to include it, otherwise I'm not going to include it. Then, as you can see here, this original image has a background, so the seed starts with at the background, and we have objects here that vary in brightness. Very bright objects are clearly easily going to be segmented. However, more darker objects can be that can be a confusion with the background. So in this case, with a lower value of criterion, what happens is that we accepted that square here that's very dark, and also that circle that's also dark. By making the criteria more rigid, such as 20, then we don't allow those to be part of the region, the background region, and then we could detect correctly the background. Other examples using the same strategy, this image here that has noise, when we define a more rigid approach or criterion for segmentation, we don't allow the noise in the background to be included in the background. Apparently, around 10 is the perfect choice, because we could, in some sense, be able to include all background, including noise, and don't include the object. However, if we increase it too much, we make the criterion so that there is possibly some pixel here that was noisy, and then allow the background to invade the inside of the object, and we don't want that in this case. So sometimes, even if we try to change and tune this parameter, the parameter would not be sufficient flexible to be adequate to the problem. For example, this image of a fingerprint, it is noisy, so when we define a criterion, for example 30, it was not able to detect the ridges here in this part of the image. When we increase it in an attempt to solve this, we end up leaking the background into the foreground or the regions we wanted to segment. So probably either the criterion used to aggregate pixels, the difference in intensities is not appropriate, or the method itself is not appropriate. So we have to go back and then, for example, consider pre-processing techniques to filter the image, or even to find or to try other segmentation methods such as thresholding.